Okay, everyone, we're gonna get started here. I would like to thank everyone for joining us today. And we have Bob Nisonger here with us, and he's going to give us a presentation on his Kite Car solar car concept. And we will be recording this session, so if anyone wants to take a listen later on, it will be available. And if there are any questions, we will have some time at the end, and you'll be able to unmute yourself and ask your question. So go ahead, Bob.
Very good. Thanks for tuning in. And thanks for this opportunity. I'm going to talk for a minute about, well, maybe a few minutes, about this kite car concept from the University of Michigan solar car team. And I worked with Arjun Ganesh on this, who is the vehicle dynamics lead on the project for the team. So we've done a fair amount of work on this, and I'm going to give you a little background, and then we'll talk about some of the evaluations that we did on this particular concept. And it says if I push this, I should be in the next group. So the University of Michigan is a perennial, and I'm talking a long time contender in the World Solar Challenge, which is held in Australia. Runs from Darwin to Adelaide, and I think I have the direction right. It's about 3,000 kilometers, and the only power allowed is the sun. They've been running this since the 90s, I believe, and it's quite a challenge. And like I said, the only power is the sun. So at the end of the day, when they get to the end of the stage, everyone's got their solar panels cranked up towards the sun, and they're absorbing some more energy, and they have a very limited battery capacity of something like 5 kilowatt hours, he said, making something up. So it's pretty much, you got to be collecting the sun to make it happen. Well, COVID canceled the 21 competition. So here we are with a whole group of these talented students just hanging around with time on their hands. Now, I know what I would have done, but they chose, to design a vehicle and go through their design process that was different from what they were used to. So it was something that, they hadn't seen, something that was a little different. And really one of their impetuses was the challenge of doing a vehicle that wasn't like every other vehicle. So they couldn't, draw on previous experience nearly as much. And they came up with was the Kite Car. Now, before we get into the Kite Car, here's the real car. This is the other thing that the team did during this, and this happened after I was going to present this at the users conference, was they built the car that was designed for 21, 8 of them here. And they first took it on a journey around Michigan. So it ran around the Lower Peninsula and part of the Upper Peninsula. And then, after that warm-up, they drove it from New York City to Los Angeles. So this is a serious bunch. They have a lot of stuff going on, and they did a marvelous job getting across the country in this thing. Again, powered only by the sun. They don't charge it up at night or anything like that. They run with this car, met the WSC rules, and they ran it WSC style. So that's sort of the team that we're dealing with here. They're a good bunch. They're doing a lot of work. And they designed a new car, and then they raced the old car the same year. So the other thing that's important is this is what the car looks like. You will see in all the graphics here another car, but that was the car that I designed. So don't worry about that. The real car is not as ugly as the one that I have. And here it is. Here's the ugly version. This is the Kite Car. So, excuse me, rather than having four wheels at the corners of the vehicle. They're arranged in this diamond or kite shape. So we've got one forward wheel, we've got two mid wheels, and we've got one rear wheel. This is why we call it the kite, is if you look at it from the top, it sort of looks like a kite. Well, I'm only going to talk about the vehicle dynamics portion of this design. Obviously, to do a solar car and to evaluate its performance, there's a lot of work that goes into electrical and aerodynamics and other systems and making things happen. But I'm just going to talk about the vehicle dynamics part here. Mostly because I don't know much about the others, but mostly because that's what we did with CarSim.
But and Bob, the motivation for evaluating this design was the aerodynamic advantage of having the wheels arranged in this fashion.
Yeah, there's a perceived aerodynamic advantage. It obviously lends itself better to a teardrop kind of a shape. Like I say, completely ignore the picture I have here. I think they can cut the air a little better and bring it back. I think it provided a little aero advantage. I think that it did do what they wanted it to do. So yeah, that was, I think, the perception. And like I say, part of the motivation was, well, let's do something different. The vehicle's traveling away from you in this picture, by the way. And the real vehicle would have all the wheels faired in, and you would see what stuff hanging out. It's nice to look at it, be able to see the wheels when you're doing the simulation work so that you can visualize what's going on. So the first thing we had to do, well, not the actual first thing, but the first thing in CarSim was we had to figure out how to build a kite car. CarSim has a couple of axles and you have to kind of think a little bit about it. So it required a little bit of tweaking to the model. This thing has an extra axle right in the middle, more or less, with two wheels on it. And it has two on-center wheels, front and rear. So it doesn't really fit the paradigm that CarSim is designed for. So here we go.
Do me a favor, real quick. You can click on the orange tab to make that go away, so it doesn't block your slides.
This one.
Yeah. Yes, sir.
I'm getting instructions here.
The down arrow. Maybe.
Down arrow? Oh
Wait,
no, up arrow.
Sorry, ignore me.
I'll be ignoring Damon now. Oh,
There we
look,
go.
look, it just slipped away. So this is sort of what you start with in CarSim. I mean, this is the design point. And we need to get to this design point over here with these two wheels in the middle and front and rear. We use the asymmetries that are built into CarSim, into the functions, to use or to modify the normal vehicle into the kite vehicle. Special thanks to David Hall for pointing out some of the simple ways to do this. And in yet another solar car project, he pointed to some things that would make this work. So thanks, David, and I hope you're enjoying retirement. So here's my baseline vehicle. This is just a standard CarSim setup. The corner designations there are for me and to communicate to what's going on in terms of assigning the corners, because I'm going to end up not with a left front, left rear, right rear, but rather a front and a rear and a left and a right. And I had to keep track of all this. I have a little sticky on my monitor at home that tells me which wheel is which. So the first thing, if we go back and look at this, first thing I'm going to do is I'm going to reduce the track width. because my vehicle's whole track is sort of one vehicle track, but each axle with little quotes on it is going to have half the track. So I'm going to go in here. I'm going to reduce the track width. This thing's trying to kill me. Reduce the track width from this case from 800 and some to 600 to get to a narrower vehicle. And I'm also going to do that for the front and the rear. So I'm going to shift the axles. No, so I'm going to do it for the front and the rear. So here's where we're going to go next. Come on, cursor. So we've narrowed them up. So now we got a skinny little car. Skinny, but it's still symmetric. It still looks like a car. It just happens to be very skinny. So now I've got this skinny car. So I'm going to move the suspensions side to side to get them to move by half a track so that I've got two wheels on the center line and a wheel on either side. So, so the total track width is now what the track width was in the beginning. So I've moved the wheels now by moving the track width, or by moving the suspension center lines. And now I've got something that's, well, it's probably not very useful. But it's now I've got a full track width and I've got a front and a rear that I can work with. So now we'll move the outer wheels fore and aft, shift them from their normal positions at the wheelbase to half a wheelbase and put them both in the middle. So I'm moving, in this case, I guess the left side I'm moving forward and the right side I'm moving back. So you can see that this little change here, offsetting the tables, provides me the new geometry that I'm looking for. So now I've got this. I have a kite car. So now we have the geometry. All we had to do is go in and exercise some of the asymmetries allowed in CarSim and make it happen. So now we have a car. You still have to do a few more things to make this work. We're going to have to twiddle the steering because I'm only going to steer the very front wheel, which is now the right front. And obviously you have to adjust your suspension characteristics because the front and the rear and then the two sides are probably going to be different. I keep trying to do stuff here that I can't do. So we've got a car. Yay. So now we can start working to the team's requirements. The WSC, the World Solar Car Competition, has a set of requirements. The team also has a set of requirements that add on to the WSC. I'm just going to hit some of the high points here. The WSC has a rollover resistance requirement, and this requirement in quotes, of a 45-degree tilt table without tipping over. There have been some incidents in the past, so they've implemented this. They also have some handling requirements, one of which is a turn radius of 7.5 meters, sort of a maximum turn. Low speed, obviously. They also have stability requirements. Again, requirements is a little bit of a stretch, but they want directional stability. They want to have crosswind tolerance. And in general, the teams will show this through analysis or testing. So they've got some measure of that. And they also have a braking requirement of the front wheels locking first. Yes, I'm fiddling with the mouse again. So this is an incomplete list. All these things are either directly or indirectly to the WSC. The team has additional stability requirements, and the team also has its own set of requirements on the design and the safety of the vehicle beyond those that are imposed by the WSC. So there's more, there's a great list of requirements, and this is just a tiny bit of it. So looking at these requirements in order, if we start with the tilt table, WSC uses the tilt table concept to address rollover. This is a time-honored approach and a good one. So MSC modified the truck sim tilt table to use it with CarSim. Thanks to Drew. Drew Reichenbach helped me out with that, gave me a framework to work within to have a CarSim tilt table. The other thing that WSC does is, because their cars might have 4 wheels, they might have 3 wheels, they specify the rollover resistance about adjacent contact patches. So with a standard car, you would go between the front and the rear on one side and determine your rollover resistance. And usually it's done perpendicular to the x-axis of the vehicle. In this case, they want the vehicle, they're trying to find the minimum rollover, so they're going along the contact patches. So some are going to be high, some are going to be low. So a set of VS commands were written to choose which pair of contact patches you wanted to look at. And the vehicle gets oriented with the contact patches aligned with the tilt table pivot. So let me see if I can show that to you. And then we'll see how I'm doing. Oh, come on, guys. Work with me. We can do this. Maybe. Oh, look, it's a tilt table. So you can see the car, like I say, it's not nearly as pretty as the real car, but it's on this little tilt table. And it's aligned along this axis. And I'll show you another picture of that. Yeah, so here's that same car, and you can see that here's the contact patches. It's the front and the rear, or a front and a right. And here's the tilt table pivot. So we've aligned these contact patches with the tilt table pivot. You can also, another case would be these two, and another would be these two, and then these two. So there's 4 different selections that you can make on which way you want to tilt this vehicle. And there's what it looks like when it tips over. And I think you're trying to kill me here, David. That's what I'm thinking. Oh, how do I get it back? Oh, there we go. Here we go. Damon had just about reached for the keyboard. So we got the vehicle tilting, and in the corner here are the readout of the furnace. You see one goes up, another goes up. So this is the new CarSim tilt table. I had to shorten it because it came in at about 50 meters long. But we use this to evaluate the rollover threshold of the vehicle. This one definitely does not meet it, but by increasing the track and the ball stiffness, you can approach that. So the next step was low speed turning. Now, for a conventional 2-axle vehicle, these calculations are pretty straightforward. L over R to get the steering geometry, and then you twiddle the two fronts to get the Ackerman. For the Kite, that's not so easy. It's a little more like a tandem drive axle vehicle, a heavy truck. Fortunately, this is something I have experience with, so I know it's a problem. So for a typical vehicle, you can define an instant center of the turn based on, perpendicular from the rear axle. And if it's steered, you can also do a perpendicular from the rear tire and perpendicular to the front tire. So you've got an instant center that you can work with. You can calculate the required steer angle to negotiate a given radius based roughly on the wheelbase divided by the radius of the turn. And it's a fairly good estimate for a car with good Ackerman. So, like I say, with one steered axle, we collapse the vehicle into this single track vehicle. Assume zero speed, so you assume no lateral forces, pizza cutter kind of tires. And then the steer angle is the arc sign of the wheelbase over the radius. And then again, given there's some track width, you have to modify the angles from the inside and the outside to keep the slip down. For if you got a Kite, on the other hand, that doesn't work. There is no common instant center between the three different axles because I've got two that don't steer, and that's pretty much by rules that they don't steer. Any axle behind the center of gravity can't steer. And I've got one that steers, so I end up with no common instant center. This makes this far more challenging. So this implies that you're going to have to generate slip angles, and then if you generate slip angles, you're going to generate lateral forces, even at low speed and low lateral accelerations. The definition of wheelbase gets modified because of this dual rear axle. Chris Winkler has a nice paper explaining that and how to calculate the effective wheelbase. And I looked at that and it was complicated, so I decided to simulate it instead. The effective wheelbase is going to fall somewhere between the axles. In this case, it's very near the rear axle. I have a video that I probably won't be able to make work here. But Damon's hovering. It's great. Not that one. Let's get rid of that one. Let's try another one. I could explain to you what he's doing to me here, but it would be beyond belief. You couldn't imagine it.
Just tap.
See, that didn't work.
Just tap the tab.
Oh, look, he's explained it to me. This is good. So, let me bring this. I can get that cursor back over here. So we're running around this turn at about 2 kilometers now. Really, really slow. And the 7.5 meters is the white stripe that the outside tire's on there, which shows that we actually made it. The red arrows are tire forces, and you can see that the front and the rear are both making forces towards the inside of the turn, as they should. The middle axle, on the other hand, is making forces to the outside of the turn. This is probably not the best situation. It does, however, meet the requirement. Sometimes the road stripe shows through the animation, which is kind of interesting. So I got 2 kilometers an hour, 7.5 meters on the outside. Steering angle is around 15 degrees, which is not that much. But due to that, it generates some significant slip angles and some lateral forces. And you could see the arrows there. Dave was looking at his watch, something's up. The mid-axle is generating forces that are going the wrong way. So this is a 5 milli-G turn. So this is not much of a turn. The tires are generating on the order of 0.4 G equivalent. Show you some pictures. Stuff like that. Here's the steer angle. That's not very exciting. It's about 15 degrees and small change. And here are the slip angles. And you can see that the front and the rear, which are R1 and L2, are generating forces to the right, which is and the other two are generating forces in the other direction. So I've got this huge spread in forces here. And slip angles, and here's the forces. Now the forces, you can see that R1 and R, man, yes, R1 and L2 are making positive forces, so they're going with the turn, and the other two are going opposed to the turn. Now these forces are pretty small, 215 or 200 sort of newtons, but the car only weighs 215 newtons or kilograms, so that's a lot of force. So if we normalize that, we can see that we're in the general 0.4 range, 0.4 to 0.5 and 0.4. So the thing is fighting itself, and it's really working to do this 7.5 meter turn, which should be easy. So the other thing we looked at was the understeer of the vehicle. He said moving the screen when he shouldn't be. The Kite Car is not exactly a standard 2D refueling vehicle, but the same concepts hold. The effective wheelbase may not be as measured due to the tandem effect. That's really only a low speed thing. That's sort of a baseline that you add on to calculate understeer. The general trends should be similar. And I'm taking an example here, moving the CG forward and aft. So I would expect it to pick up some understeer when I move the CG forward. I expect it to lose some when I move. In this case, I'm driving the rearmost wheel. The general plan for this had been to drive one of the mid wheels. That made all the directional responses very asymmetric because it's got some kind of yaw force from the driver. So we decided to make it easy on ourselves and just use one wheel to drive the thing. So I've got these 3 variations. So I've got baseline where the CG is near the mid axle. I've got to move 100 millimeters forward, 100 millimeters back. So here's the steer angle. And you can see that we're getting some changes in steer angle. And what we want to look at is the slope of these to get the understeer of the vehicle. So if we calculate the understeer, this is a dangerous thing. So my initial CG near the mid-axle gives me this neutral-ish kind of response here that goes oversteer. If I move the CG forward, I get some more understeer. I get up to a whopping 0.6 degrees per G here. And it also goes oversteer. And if I move it back, it's oversteer almost immediately. Instability isn't just waiting for it. There's a couple of really interesting things here. One is they all go oversteer. That's at pretty low lateral accelerations. this fixed mid-axle becomes destabilizing because of its location. It becomes less destabilizing the more you move it rearward. Ultimately, you can turn this into a tricycle, the wheels at the rear, and it would probably still go oversteer. But it would have more understeer in the beginning. You get the kind of influence you'd expect, and that as you move the CG back, you get more oversteer. So, like I said, moving the CG has the anticipated effect. Everybody's oversteered high acceleration. Getting out of that there wasn't really a way to develop out of that. The mid-axle doesn't do much for yaw stabilization because it's so close to the CG, it really can't make any yaw moment. It also carries all the load transfer. So what little it's doing, or in either direction, does go down with lateral acceleration. The front and rear axles show the typical kind of load sensitivity trend. That is, as you load them more or less by adjusting this spring platforms or something, you'll see the change. The change in the front wheelbase is interesting. If we go back a couple here, when we look at the steer here, you can see that at low speeds, low lateral acceleration, the moving the CG backward makes the wheelbase look longer, and when it forward makes it look shorter. And that has to do with the load distribution front to rear and how you twiddle that. Because you do have all this force to deal with. And again, the mid wheels turn opposing the turning at low speed. That's just one of the shortcomings here. So, give you a quick summary here. The University of Michigan Solar Car team analyzed a unique vehicle configuration. I mean, like I said, they wanted to do something different. This configuration, the Kite, provided some significant vehicle dynamics challenges. First, we had to do some modeling tweaks to CarSim to make it happen. Rollover resistance was a big deal because it was really difficult to get there between the fact that it's sort of like two three-wheeled vehicles backed into each other. It's also got all this rollover resistance in one axle that's in the vehicle geometry and the resulting slip angles and forces give you some interesting low-speed turning issues. Like I say, it would pass the requirement, but it was making a lot worse. Vehicle directional stability was also a significant challenge. You could get some understeer in this, but it was gone by the time you got to any kind of lateral acceleration. So the whole design process was completed and reported, and now they're on to the next challenge, which is the 2023 WSC. And I don't know what we're currently in the process of doing a concept selection so that a vehicle can be built.